Okay, so we have discussed about the way to visualize the intermediate layers or the first layers and so on in the previous lecture. But now let's see the last layer, which is always a fully connected layer. So when we say the last layer, it's not the classifier layer, but the layer before that. So typically in a neural network, we have something like this, right? So you have an image that will be passed through a convolutional kind of layers, and then we will have a fully connected layer, and then we have a final layer. So maybe this layer will be something like 2048 weights, and this will be like 1 cross 1000 in the case of an ImageNet set. So what we are talking about is not this classifier layer, but this last fully connected layer is what we are going to look at. And while we discuss about the visualization of this layer in a moment, it's actually an interesting factor, because what we are seeing over here, so let's say the input size is 224 cross 224, which is kind of a standard size, and of course it's a color image, so it's a three-dimensional input which is going in, and this is getting converted to something like a vector of dimension 1 cross 2048. And what's exactly happening is an image is kind of represented as a vector, or we call this as an embedding of the image, okay, a representation or an embedding of an image. But the problem is this is actually a high dimensional space, because you have 2048 dimensions here. And don't get confused, because this is for a single image. If you have 1000 images pass through, you will have a size of 1000 cross 2048, and that's a huge dimensional space even for us to think about displaying it. But there are ways to display it, which we will talk in the next slide. But before that, we are going to use this particular guy, this layer, for something interesting. Okay, so let's say I have a data set of images, and in that images I'm very sure that it will have flower images, it will have elephant images, it will have sheep images, it will have these Halloween images, and it will have dog images. So if you are given a challenge to cluster these images into these groups, for example, you want to form clusters which will have only flowers, clusters which will have only elephants, and so on, we can actually use this guy, this last layer, for that purpose. So one very trivial way or very crude way to do this is, you do take one image as a template and then correlate all the images in that data set with that particular image. So this can be symbol correlation, or it can be something like a structural similarity index between that reference image and all other images. But the problem there is, the images in your data set may be having some color intensity variations. Maybe some of them are black and white images, or some of them are taken in a different background. So then the chances that the clustering will happen with symbol image based correlation or image based similarity is very, very rare, and it may fail utterly. So for example, here if you see these two images, this is having a kind of a brownish background, and this is having a green background. If we try to see the similarity between them, it most probably will be very less. So the best option for us is, like, you pass all the images through a network like this, and then go to this space where the image is represented as a vector, or as an embedding. Now what you need to do is just do the similarity on this embedding and not on the actual image. So basically you pass this image, gets its the feature space, and you pass this image also, you get the feature space, and then you do a L2 distance, or mean square error distance, between these two, and that, or maybe a cosine similarity between these two. That will show you kind of higher value than if you directly correlate the image. So the idea is pretty simple. You pass all these images through the network, gets its embedding space, and then do the L2 similarity between them, and group them according to that similarity. If you do that, that's what this paper did. You can actually very easily cluster the similar images together as seen over here. And this can be very useful in the case of uh, a clustering problem, something like a self-supervised clustering problem. All you are going to do is use the trained neural network and extract the embedding layer, so that you have a nice vector representation of your image. Only thing you have to bear in mind is, beware, you should not be doing this on the last layer or the classifier head, but on the final fully connected layer. Okay, so that's very important. So I was talking about earlier that 1248 or even 1496, for example, in AlexNet, that's the final feature layer. How do you display that? How do you visualize that? So that's not really possible, because if you have 1000 images, this will become something like 1496 or 1000 2048. these are very difficult to kind of visualize. So what we are going to do is we convert this into something like 1000 cross 3 or 1000 cross 2. So three-dimensional space or two-dimensional space. If it's a two-dimensional space or a three-dimensional space, you can actually display them in the form of a scatter plot, and that's what exactly doing this. But how do you do this? This conversion from a high dimensional space to a two dimensional space. For that, you're going to use many techniques. Are the two of the popular techniques are, one is the principal component analysis, which is actually quite interesting, and the second one is T distributed stochastic neighbor embedding, which is kind of a manifold learning technique, which is also popularly known as the TSNE. And both these are very interesting techniques, and it will take some time for you to understand. I'm not going to explain these techniques in this lecture, but please feel free to have a look at this if you are interested in doing a deep dive. So let me remove all the ink here, and if you see uh, the TSNE representations of two cases here. So here what I'm going to do is a ResNet 50 model which was trained on the ImageNet dataset. I directly apply on the 200 class BERTS dataset which we employed in the lab. If you do that, you get obviously something like, let's say I have some 1000 images, I'll get obviously something like 2048 if I'm using a ResNet 50. And if I do a TSNE and have a two-dimension thing, you have 1000 cross 2 as the output, and if I display it, it looks like this. So the problem, the color that is shown over here are the different classes, the 200 classes. But the problem here is it's not really clustered that well. You can see few clusters here and there, but it's otherwise not that great. The moment you do a retraining of this ResNet 50 on this data set, like the experiment that we did in the lab, and then apply the same concept of TSNE 2D compression and then plot it, you get much better result. You compare these two, you can see the clusters are formed in a much better way. Even though we could still improve the result, the clusters are not very evident. Ideal scenario is well formed clusters and most of them widely separated, then it's a very good classifier network. So in a way, this is actually a good visualization tool to see whether your network has learned nicely or not. If you're seeing something like this, obviously it's a very bad thing. If you're seeing something like this, it's okay, it's better, but you can still improve on top of it. So the underlying story is the last layer, not the classifier head, but the final fully connected layer is something known as the embedding space, or some people call it as the bottleneck layer, or the common name is the fully connected layer at the end. That is actually a feature space, very useful, which is actually a vector embedding of your image, and that can be used for similarity purposes. It can be used for visualization just like this to check uh, the the good quality of your classifier uh, and so on. So it's actually very useful for many purposes. So again, Andrich has created an interesting visualization. So instead of having point clusters like this, can I get the original images corresponding to this point and then put in that position? So if that is possible, it's actually an interesting scenario which is shown here. So different resolutions are possible. So let me go to the highest resolution. So what you're seeing over here is a cluster similar to what we saw earlier, but he has actually put the original images here. So you can see here the vehicles or the buses are clustered here, and if you go here, some buildings are clustered here. If you go to the bottom, some dresses are clustered here. So that's interesting, right? Instead of simply showing it as a point cluster, can you put that original image in that position and view like this? It makes a lot of meaning to it.